So good morning. We are starting the second networks topic. We haven't actually finished all of the first networks topics. We've got two lessons today. We're going to be doing networks 2 this morning, and then we'll build on that by looking backwards to some stuff that we missed at the end of year 10 this afternoon. So you said the thing that you're most confident at is what we covered last year, all about cybersecurity. I know some people are very interested in that topic in this class. The thing that we're least confident at is not something we're covering today, but we will come back to it. It's all about the shape and the connectivity, the way that networks are connected together. Today, we're interested in the first learning objective in this progress checker, which is all about embedded systems. So let's have a quick look for some definitions. We want to make sure that we know what an embedded system is. I said last year, well, not last year, in June, lots of year 11s, last year's year 11s, missed out on just a 1-mark question for not getting the definition correct. We want to make sure that we know what a general purpose computer is and how it differs to an embedded computer system. We need to know what the hardware and software looks like in an embedded computer system, its similarities and differences to a general purpose computer, and know what they can be used for. So we know that a general purpose computer, or just any computer, has to have input and output with some form of process inside, and that's normally a CPU, and it needs to store stuff. Usually it has some secondary storage like a hard disk or a solid state drive or something like that, but it absolutely must have some primary storage, some RAM. General purpose computers like the one sat in front of you at the moment, but it could be a laptop or a smartphone or a tablet. It's general purpose because you can use it for almost anything. You can put different applications on it and you can use it for work or play or communication, depending on which application you put onto it. There are some computers that perhaps don't look like the computer that sat in front of you that aren't general purpose but still have input, process and output. So I got some new earbuds, which I think are just like a hearing aid really, because they've got some fancy kind of thing that allows me to wear them whilst I'm running or cycling, and I can still hear the outside world if I want to, or I can shut off the outside world if things are too noisy and I just want some peace and quiet. But a hearing aid is not a general purpose computer, but it is a computer. I had some big faffs with the dishwasher recently. Really proud of myself that I managed to fix it, and for the first time in a couple of weeks the dishes are actually clean rather than having to take them out of the dishwasher and wash them by hand. But there is a computer that you can program with inputs. It will do a process and it will have outputs of hopefully clean dishes, and the same kind of thing for the computer here. These are not general purpose, they're specific purpose, and they are embedded into a particular physical device. Embedded means they live inside. So a traffic light system is embedded into a single thing. It's not portable, it stays there. It does one job and it does it well. You don't have an app store on the traffic lights. You don't want to make it open to the outside world to hack into it. You don't want to install software updates while people are waiting to see them. It does its job and it does it well because it only has one job to do. You program it in the factory, or maybe somebody comes with their laptop and plugs a cable in to update it. Otherwise, it just does one job. So what are the characteristics? A specific purpose, usually a single purpose. That's different to general purpose because you don't have an app store. You can't replace that purpose. The computer in front of you will cost quite a lot of electricity, especially this year, to run it. An embedded processor often uses maybe 10 times, maybe 100 times less power to run. An embedded process, an embedded computer, or a single board computer often, is much smaller physically. It requires less maintenance. It's usually much cheaper. And it's much, now I'm not going to use the word faster, it might have a slower processor, but it responds much quicker. How does it manage to do that? Well, if you think about the navigation system, that as long as you don't believe the conspiracy theories, landed people on the moon the first time round, that was less powerful, a lot less powerful than your smartphone. Probably less powerful than your smartwatch. But it managed to do its job really well because it only did one job. It didn't have to constantly swap out to check emails and check for updates and process all sorts of other stuff. So you can have simpler devices to do one job and to do it well. You might have all sorts of specialist sensors. This is an embedded system because the processor, the battery, the screen, the input devices are all embedded into the same physical device. And the software is kind of halfway between software and hardware, because it's not software that you install with a DVD or a CD or a USB drive. If you don't download it from an app store, it might be permanently stored on a chip on the device. It's not physical hardware. You can't see the chip and the actual storage, but it's a cross between hardware and software. It's not modified very often, so we call it firmware. Firm because it's both hard and soft, which means put on in the factory, only ever modified once, or perhaps the occasional update. We call it firmware. All right, so you should now have P1 activities. We can find this in half term 7 on the VLE. We'll watch the video. I'll pause the recording. If you're watching this at home to catch up, then you can watch this yourself, but we'll watch it together. So after you've watched the video and filled in the gaps, it's down to you to do activity 2. You can find the link here, or any other link if you want. Find examples of embedded computer systems used in vehicles or toys or buildings. Just one sentence will be fine. So the type of thing we want to try and write in here are what are the inputs, what's the process, and what's the output. For example, fashion, the input could be when it detects that you move. The outputs would be like little flashing lights built into your sequin top so that it looks really sparkly. So hopefully you've had enough time to go through most of these things for activity 2. Do go away and research all of these. Interestingly, it's these two that tend to be the focus of cybersecurity attacks ever since Stuxnet. There's been a huge realization that as we use fewer manual control systems like levers, switches, things that you can turn, and more embedded control systems, people don't want to have to drive over to those embedded control systems and push buttons. They want to do it remotely because it's easier, and you can have one technician who controls all of your factories all over the world instead of employing lots of people on a high salary. You can think of obvious downsides, because if somebody can remotely control of these things, then that's potentially open to cyber attacks. And there have been some documented cases of how easy it is to make a power station explode or shut down as a result of a attack. So lots of interesting jobs at the moment. Stress testing and penetration testing, national security to make sure that it is safe and secure. Then we move on to a particular example, so an embedded computer system inside a washing machine. It is still possible to get analog washing machines, but they're very, very rare nowadays. They all tend to have a digital controller inside. So you have to try and work out all the different components and describe what they do. So the terminology we use, a sensor is something that senses. So it might be a button, or it might be a temperature sensor, or it might be a moisture sensor. An actuator is something that changes the world. It doesn't sense, it's the opposite of sensing, it's influencing. You actuate change. So it might be a lock, it might be a motor to make the drum spin, it might be a screen, it might be a little light, something like that. So that's our next job. I would like to show you something to investigate once you've finished. So we've got a couple of these Grove beginner kits. I know some of you did work experience at the University of York and you experimented with some Arduino kits. This is the same kind of thing, but it's got all of the devices like hard wired in. You can snap them off if you don't want them. It's just really this chip that does all of the work. This is just lots of connections for the chip. So an Arduino is a microcontroller, an open source microcontroller that you can use for all sorts of projects. They're quite cheap. They're only a couple of pounds instead of like the hundreds or thousands of pounds for a general purpose computer. And you can connect whatever devices you want. Like if you were controlling a washing machine, you could have a system that has a little display, a little alarm to tell you that it's done, beep, beep, beep. A temperature sensor to check. Like you can plug in anything and write your code for it. The idea is you can use open source tools like the Arduino IDE and then send your code to it. So in theory, this code, if we send it to this little Arduino, you write it on your laptop or your desktop. That code generates some firmware which is stored in flash memory on the Arduino, and it will flash this LED. So not very exciting. Let's speed it up. Let's make it wait for less time, and hopefully when we upload it, this light is going to flash faster. Not particularly exciting yet, but the possibilities are endless. You can control a so this is flashing because it's being programmed. There we go, it's flashing faster. I saw someone program a cockroach. Did I tell you about this last lesson? Someone had an Arduino, well, similar to an Arduino, an ESP8276 or something like that, which has built-in Wi-Fi, but works using the same software and IDE as an Arduino. And you could write code to it to send digital pulses to control a cockroach's body, so that you could send a little cockroach with a sensor on into a nuclear power station to read nuclear meltdown, so you don't have to risk technicians. But also terrifying, because a human is controlling an animal, which I think is rather scary. Or if you don't have access to this and you want to play around with it, this website is absolutely phenomenal. Wokwi, sorry. And you can simulate Arduino stuff. There's all these projects that you can play around with. I'm showing you Flappy Cat on a TV. This is all written in Arduino, so it's kind of a C-style language. And you can simulate it. If you have an Arduino Uno, you can run it physically on an embedded computer, or you can simulate it. I'm not going to turn the sound on because it's rather irritating, but if you had an Arduino Uno, like the Grove stuff that I showed you, that is an Arduino Uno, and you plug in the wires and the same connectivity to a TV, it would actually display this on the TV. I think that's phenomenal. Really, really powerful. Your general purpose computer is simulating the embedded computer, running this code in real time. Phenomenal bit of coding for this website. Really speeds up the development. You can also simulate like hardware devices, like an LCD screen. Those of you that work experience at the university will have done this, I think. And you can simulate it. The code is running on here, so you can change it, hopefully. Hello, Mr. Dring. There we go, complete narcissist, want my name in there. There we go. It actually simulates the code and runs it on here. So clever. I was looking for, well, I saw some job adverts for the type of thing that you could use embedded systems, programming FPGAs, writing the code for this kind of stuff. Easy 60 grand in York, working from home partially, good job benefits, some very, very exciting jobs in this field for people of any gender or background or race. So your job, please, finish off your P1 worksheet, and then your extension today, have a look at Wokwi, play around with some of the simulations, and prepare for your minds to be blown. This is what I did my degree in, and I absolutely loved it. Find this stuff really exciting. Thank you. So if you've experimented with an online Arduino simulator, I want a screenshot, preferably with an annotation of the code that you've changed to see how it works differently. Save that Word document, and upload it to Half Term 7 Networks 2. You should have a couple of minutes left at the end of the lesson, so you can go back to your Networks 2 revision quiz 1, try and do a couple more questions before I see you this afternoon.